Hello everyone, my name is Aditya Nair. I'm an assistant professor in the Department of Mechanical Engineering at the University of Nevada, Reno. In this lecture, I'm going to present an overview of techniques required to generate fluid flow data. Now, the fundamental basis of fluid dynamics is conservation laws. These conservation laws are grounded in physical principles and are the backbone of our understanding of fluid flow behavior. The first law is the conservation of mass, which states that mass entering a control volume must be equal to the mass leaving, assuming there are no changes in mass within the volume itself. So mathematically, this is written in terms of the time rate of change of density is rho here, and the divergence of mass flux on the left-hand side. You can think about divergence as being outgoingness of a particular quantity. And because you want to maintain mass balance, the right-hand side of this is 0. Next is the conservation of momentum. This is well articulated through the Navier-Stokes equation, which balances the forces on a fluid element and its time rate of change of momentum. In simplified terms, this is the Newton's second law, with the inertial forces of the fluid balancing the pressure, viscous, and external forces. The third one is the conservation of energy. This is the balance of internal, kinetic, and potential energy, as well as heat generated by viscous forces and work done by pressure and other external effects. So now that we have learned something about conservation laws for fluid dynamics, we are going to focus on a unique perspective of viewing the fluid flow as a dynamic system. Now, the state of the system is typically described by quantities like velocity, temperature, pressure, density, all the data that we will collect using data generation techniques that we will describe soon. Now, the dynamical representation describes the evolution of these states, which is given on the left-hand side. So this is dou x by dou t. And on the right-hand side is the dynamics of these states, which is given by a function f. Now, these dynamics are a function of not only the time-varying states of the flow, but also certain parameters and also effects that contribute to the dynamics in terms of stochastic effects and so on. Now, we can also describe the relation between the output measurements of the system, which we will call as low-dimensional observables, like drag, lift, and so on and so forth, through this mapping function or measurement model H. Okay? This measurement model is usually a function of the states as well as some measurement noise that you had when collecting the data. So given these two representations and the initial state of our system, we can use this dynamical system representation to predict how the fluid flow will evolve over time. So in the last slide, we talked about parameters, but I didn't give you any information of what these parameters are. Now, in fluid flows in general, these parameters are called as dimensionless numbers, and they can provide some valuable insight into the characteristic of the flows in different flow situations. The first parameter that we are going to discuss is Reynolds number. Now, Reynolds number is the ratio of the inertial forces and the viscous forces. And it typically tells us whether the flow is laminar or turbulent. So a high Reynolds number is associated with turbulent flow, and a low Reynolds number is typically associated with laminar flow. The other parameter that is used in fluid flows is Mach number. Now, this is the ratio of the flow velocity with the speed of sound in the medium. So this quantity is typically used in compressible flow or high-speed flows, and it is important to understand situations where discontinuities of the states of the flow may arise. Now, I want to make a quick note of the distinction between incompressible flow and compressible flow. Incompressible flow implies that the density remains constant within a parcel of the fluid that moves with the flow velocity, while in compressible flow, this density can change over time. So let's look at an example of flows with different dimensionless parameters. In particular, we'll be looking at different Reynolds numbers. Now, here on the left is a flow over a sphere with a Reynolds number of 20,000. And you can see a lot of flow patterns behind the sphere. In fact, there is a lot of large scale structures in this flow. But when we increase the Reynolds number to 200,000, we see that for this exact same configuration of the flow over the sphere, you start to see really small structures emerge. And we can't make out the large scale pattern anymore that we were observing in the left. So different dimensionless parameters can dramatically vary the fluid flow behavior. All right, so in this slide, we are going to talk about two main techniques for generating data for unsteady fluid flows. The first one is computational fluid dynamics, which is a set of numerical algorithms used to solve, analyze problems in unsteady fluid flows. In particular, they will solve the governing equations that we talked about before, or the conservation laws. There are different approaches for performing CFD. The first one is direct numerical simulation, which resolves all the scales in the flow, and it gives the most accurate and detailed representation of the fluid flow physics. But there is a caveat. It is computationally expensive. The second one is the large eddy simulation, which serves as a good middle ground. It resolves the large scales of the flow while modeling the small scales. The third type of technique that is used usually in CFD is the Reynolds averaged Navier-Stokes equation, which models all the scales of the flow, making it suitable for high Reynolds number problems. Now, the caveat here is it provides less detail about the flow physics. All right, so now that we've discussed the computational or numerical techniques, there are experimental techniques that we can use to generate data. In particular, particle image velocimetry, or PIV, and particle tracking velocimetry, or PTV, are optical methods that are used for visualizing and measuring the velocity in the fluid flows. Now, how are they done? They involve seeding the flow with some particles and then tracking their motion with high-speed cameras. Some other techniques include the laser Doppler velocimetry, which uses a Doppler shift to offer laser beams to measure the flow velocity, while hot wire anemometry uses the cooling effect of the fluid on a heated wire to determine the speed. Now, both CFD and experiments are complementary to each other. In fact, we need experimental data to validate and verify some of the numerical algorithms. So they are both complementing each other in terms of the physics, and they have a lot of respective strengths. So they're best used together. So a typical pipeline for performing computational fluid dynamics is to create a geometry that you care about, then mesh a computational domain with grid points, and then discretize and solve the governing PDEs, or the conservation laws that we discussed before. Experimental techniques require a lot of careful instrumentation and calibration to make sure that it captures the underlying physics well. All right. So we discussed about CFD techniques as well as experimental techniques. So from these techniques, we are going to get some data. Now, this data can be mainly divided into two types. It's either high-dimensional snapshot data or flow fields, or low-dimensional observables or measurements. Typically, the high-dimensional snapshot data involve variables like velocity, vorticity. Vorticity is nothing but the curl of velocity or the rotation of the fluid elements. You have pressure, density, temperature. These are all the different flow variables that are involved in the governing equations that you can extract as data. So shown on the right is a typical contour of vorticity in a flow past a cylinder, and you can see these different structures of yellow and blue, which indicate opposite signed rotating structures in the wake of this cylinder. For low-dimensional observables or measurements that we can measure the lift and drag coefficient that the body experiences, which is computed from the lift and drag forces. So the lift force is the force opposing the weight of the body, and the drag force is the force opposing the thrust of the body. We can also measure strains and deflections of the body, especially if the body is flexible, that we are talking about, embedded within the flow. We can also obtain local measurements of pressure, velocity, acoustics, and so on and so forth. So there is plenty of both local and global measurements that we can get, that we can use for our data analysis, that we classify as high-dimensional or low-dimensional observables. In this slide, we are going to talk about how to organize all of this fluid flow data. So you got this data from experiments, you got this data from computations. How do we combine and organize this data? So we're going to call the high-dimensional snapshot data that we collected as X and the low-dimensional observables that we collected as Y. For both X and Y, each column is going to represent the time evolution of the data, right? So we collected some measurement at one time instant, then we collected at a separate time instant separated by a sampling time step or a period. So we're going to collect these different realizations, and we are going to stack these snapshots or observables that we collected over time as columns. Now, for X, we must organize both the high-dimensional data over the spatial points as well as the different variables that we collected over these spatial points. We are going to organize them such that all the data over the spatial points for one variable are going to be stacked first, and then we are going to similarly stack all the other variables. So each row of Y denotes a particular measurement or an observable, and if you have multiple measurements, which we are calling as features, you can stack them as rows. So I want to note again that the columns are time and the rows for X are spatial points and then different variables with the spatial points, and for Y they are the columns are time, but the rows are different features or different measurements that you collected. All right, so let's do a quick recap. What did we talk about in this lecture? We talked about conservation laws in fluid dynamics. We discussed some techniques to generate fluid flow data, and then we discussed how to organize the data that we got from either computational fluid dynamics or experiments. Next, we will talk about methods for dimensionality reduction of these high-dimensional flow field data so that we can analyze them in a more simplified manner. See you there.